Ions. Okay, ions are what we're talking about. Ionic radius, so same idea. It's the size from that nucleus to the outermost energy level. But what's different now with ionic radius, or ions? What's changed? The charge has changed, which means what else has changed? Yeah, number of electrons have changed. Okay? So, a couple things. Just memorize them. Cations, they are the positive ones. Remember, they got that positive plus T there that looks like a plus sign. Positive ions, guys, they lose electrons. Therefore, they're going to be smaller than their parent ion. Okay, they're going to be smaller than the parent ion. Anions gain electrons. Negative ions, they are larger than their parent ions. So let's think about why that might be. Any idea?
Have more electrons.
Which one are you talking about? Anions, okay. Why are they bigger? Because so having more electrons, like you said, if these have more electrons right here because they gain them, why would they be a bigger size, guys? Alex? They have more stuff. Okay. Okay, so just by adding more things, you're going to get bigger, yeah? That's going to be part of it, but there's another reason why as well.
They're negatively charged.
So them being negatively charged, what is that going to force them to do in that ion?
I don't know.
They're going to spread out. Why are they going to spread out? You're getting there. Because
same things push apart.
exactly, guys. Like charges will push apart. Absolutely, you guys all got there together. That's awesome right there. Okay? There's more negatives, so that's going to be, just having more stuff is going to make it bigger. That's one way to think about it. But if we go deeper as to why, it's because those negative electrons, you have more of them, they want to spread out even more. Okay? So let's take a look at an example. We're going to do an electron configuration here for a couple of them. So let's do chlorine and chlorine ion. Okay? So chlorine, if we do it out, it's going to be like, neon. And then it's 3s2, 3p5. So how many electrons does chlorine have total? So we're having your reference packets out, your periodic tables. Always have those out. 17. So we have 17 electrons here. How many electrons would we have in the chlorine ion? 18, right? It's got that negative 1, so you add it. We've got 18. So now our configuration is going to look like this. 3s2, 3p6, because we got that extra electron. Okay? If we were to draw a Bohr model, again, we don't use the Bohr models a lot for pictures, all right, but we're going to do it just for the sake of showing you guys what's going on. So there's 2 electrons in that first energy level, then we can hold 8 in the next energy level, kind of like our Lewis dot diagrams. And then we have 8 out here as well. 2, 3, 4, 5, 6, 7. That's what chlorine might look like. Again, this Bohr model, guys, is just as a visual representation. As soon as you bring in that other one, now you have another one, so you are offset. We have 17 protons in the middle that are holding them at one distance, but as soon as we bring in that other electron right here, okay, it starts to spread out just a little bit. Now, is it going to be a lot? No, but it's still going to be enough to make it a little bit bigger. Okay, so however you want to remember it, what it comes down to is that nuclear pull now is not even with your protons and your electrons, so they're going to be able to spread out because there's more negatives. Okay, on the flip side, with those cations, okay, let's go and take a look at those. So let's look at sodium, for example. Sodium and the sodium ion. How many electrons does sodium have? 11 electrons. Sodium ion, if it's a +1, it's going to have 10 electrons. So if we go ahead and we write it out, okay, that's going to be 1s2, 2s2, 2p6, 3s1. Grant? Yeah. All right, sodium ion, we have 10. 1s2, 2s2, 2p6. Is that it? What else did I get rid of right here, guys? What's the difference here? Now, why it makes sense even more with the cations that they get smaller is because a lot of times they're going to lose. What do they lose here? What does sodium lose when you look at it? What do you say? Yeah, it loses an energy level. That should be easy to see with those positive ones, the cations. They lose an entire energy level because now we're only up to 2p6. Okay, it's got the electron configuration that is neon. Right, so we lost that entire energy level, and that's why cations get smaller. So they typically will lose an energy level. Anions stay at the same one, but they get that extra electron, so it spreads out just a little bit more. So it's a much bigger impact for cations in their size than anions. Here is a visual representation to show you this. So these are positive ions, guys. These are cations. You can see that there is a huge difference in the size. And again, why is that? Because they lose a what? They lose an energy level. Okay? So we can see that, hey, group 1, they get a whole lot smaller when they go down. I mean, we're talking almost 1 AMU. Not AMU, 1 picometer, I think, is whatever the unit is here with this. Angstrom, that's what I'm thinking of. All right? Whereas ionic radii, depending on how many electrons they get, they can change more significantly. So like nitrogen, it gains 3 electrons. It's going to spread out a lot more than, say, fluorine's difference is not as big, but it's still bigger. Okay? Whatever it takes for you guys to remember how they are, commit it to memory. If you want to just memorize 1, cations lose it, they get smaller. You got to know anions are going to be the opposite. Okay? On your test on Tuesday, I will give you sodium and sodium ion. Which one's smaller or which one's bigger? And you're going to circle which one is smaller or bigger depending on the question that's asked. Okay? It's one of those things, there's no arm motions with it. You've got to just know it. But think about what's happening, all right, with those electrons. It goes back to that nuclear pull. Okay? The nuclear pull is what governs all of these trends. So that's ionic radii. You will see, there's a good chance you could see a question or two like that on your Regents exam in June. The last thing we need to talk about is reactivity. And again, that's the ability of an element to react. We've talked about this a little bit, guys, when we did chemical versus physical changes. All right? Reactivity is one of those chemical properties. All right? But we have 2 separate trends here. You've got to know one for metals and one for nonmetals. So, metals, where are metals located on your periodic table? What separates the metals from the nonmetals? The metalloid staircase, okay? So just in general here, now you were right, Joe, when you're saying kind of the middle. When we talk about where metals and nonmetals are located, it's in reference to that staircase. So to which side of the staircase are our metals? The left, right? Because what is in the big middle block there? What are they called in groups 3 through 12? Transition what? Transition what? Oh, there you go, metals. He wasn't even here and you got it. There we go. Guys, it says it right there, metals, so you know that to the left should be the metals, okay? And then nonmetals are to the what? Right, okay, good. Now, their reactivity, guys, is going to be different because they've got different properties, okay? And this is where your arms, the move, really comes into play here. When we realize that, hey, the bottom left corner is where the metals are, and then the top right is typically where the nonmetals are, the opposites. When you put your arms together and you look at your elbows, okay, where do you think the most reactive metals are going to be? It's not a trick question, actually. The elbows, guys, where your elbows are, that's where you're going to have the most reactive metals and nonmetals. Okay? So the most reactive metals are where? To the what and what? To the left and down. And then the most reactive nonmetals are going to be to the right and the top. Why do I have this statement here saying that except noble gases? Why don't they react? Absolutely, guys. They already have 8 valence electrons, therefore they don't react. So what is going to be the most reactive nonmetal out there? Fluorine. Guys, fluorine is the most. Remember, chem is Fon. Those are the 3 most reactive nonmetals. Okay, because again, it goes back to electronegativity here. Okay, the most when you talk about nonmetals, you look at the highest electronegativity, and it's going to make it more reactive. Why? Because what does electronegativity mean? The attraction of an atom for what in bonds? Electrons through bonding. They're the ones, guys, who want to pull those electrons in to get to 8 because they're so close. All right. That's why noble gases will not react. So if we take a look here at this graphic, Metal reactivity increases to the left and down. So francium is going to be your most reactive metal. And then fluorine over here is going to be the most reactive nonmetal. Okay, opposites. Remember, there's patterns. This whole unit is all about patterns and being able to see it with the periodic table. Okay? So if I ask you something like, what's the most reactive metal family? What would you tell me?
Alkali metals.
The alkali metals. What's the most reactive nonmetal family? The halogens, not the noble gases, okay? So when it talks about reactivity, guys, and electronegativity, they go kind of hand in hand in terms of the nonmetals, all right? The noble gases, they are non-reactive. They're just chilling out saying, hey, man, just take it easy. They're like, the hippies, just, level, even keeled, okay? Where the other people, fighting for everything, all right? They're just like, hey, just relax, all right? Because they already have those 8 valence electrons. Questions? All right, that kind of sums up, guys, all of our trends. It's up to you now to know what they are, to find ways to remember those. Remember, the arms are one of the best things. What arm do we use? All right, using my left arm, what trend follows my left arm? Atomic radius. Which way do I start my arm? Is it up and down or left to right? Up and down. For atomic radius, it's up and down, and then I drop it left to right. That follows atomic radius. And then everything else is my what arm? Right arm. And which one is more important, left to right or up and down? Horizontal or vertical? Horizontal. So if atomic radius, guys, memorize that one is up first and then down. The other one is just the opposite. Okay, I'm going to have you guys do some practice.